4.2 Logarithmic Function Preparation Part 3. So, a little bit more practice, but we're going to be going over some radical rules. So if I multiply two radicals together like this, for instance, the cube root of x to the second power multiplied by the fourth root of x, normally we wouldn't be able to multiply these together because we only get to multiply two things together, or two radicals together that have the same indexes, in which case you multiply the things underneath the radical sign, the radicands, together, right? But you can't do that in this case because they don't have matching indexes. So we have to use a different method to solve this, right? Or to simplify this. And the way we do that is if we can make everything, if we rewrite everything in terms of exponent form, right? So x squared, okay? But because this index is 3, I'm going to put the fractional exponent as 2/3. Then I'm going to multiply that by x right here, but that's going to be to the 1/4 power. And now, because they are both in exponential form, we get to use the product rule of exponents. So we simply add these exponents together. So we would simply say 2/3 plus 1/4. And that would give us, well, first of all, we have to simplify, so a little bit of side work. 2/3 plus 1/4. Now, we need a least common denominator of a 3 and a 4. In this case, it's going to be a 12. So we need to multiply 3 by something to get it to turn into a 12. So we multiply that by 4, which means we also multiply the numerator by a 4. We multiply this 4 by 3, which means we multiply the numerator by a 3. And that gives me 2 times 4, which is 8. And this gives me 3 times 4, which is a 12, plus 1 times 3, which is a 3, 4 times 3, which is a 12. So 8 twelfths plus 3 twelfths gives me 11 twelfths. So we end up with x to the 11th twelfths power. Now, we could write this as a radical answer as well, which would simply be the 12th power of x, and then we bring the whole thing to an 11th power like that, right? Now over here, normally we wouldn't be able to combine these, like write this as one giant fraction, unless these were both the radicals had the same indexes, but in this case they had different indexes, so we have to use a different method. But again, the first step in this one is to turn these radicals, right, into fractional exponents. So we would say x to the 3/2 power, and this would be x to the 2/3 power. Now, because we're dividing, we're going to use the quotient rule, so we would end up with x to the 3/2 minus 2/3. Okay, now, these are not like fractions, meaning they do not have the same denominator, so we have to do a little bit of side work and make sure they have the same denominator. So we have 3/2 minus 2/3, right? Now, the least common denominator is a 6, so I multiply the 2 by 3 to turn it into a 6. And we multiply the numerator by the same. We multiply this 3 by 2, and we multiply this one by the same, a 2. And that gives me 9/6 minus 4/6, which gives me 9 minus 4/6, which gives me 5/6. Okay, so we go back over here. That means I end up with x to the 5/6. And that's it. Now you can also write this as a radical if you wanted to. So you can put the x underneath here. So that would be a 6th power. I could even bring the whole entire thing to the 5th. Over here, we have a square root of a 4th root of z. Okay, so just like the other previous two problems, we're going to convert everything to exponent form so that we can do something with this. So normally there's not a whole lot we can do with this, but this is really saying, for instance, we'll start with the middle, which is z, that z is to the 1/4 power, and the whole thing is to the 1/2 power. Now, a 1/2 power of a 1/4, this is the power rule, so we end up multiplying those together. right? So we end up multiplying these together. So we'd simply say 1/2 multiplied by 1/4, which gives me 1/8. So it's z to the 1/8 power. And we could write this as z, and we could simply say it's the 8th root of z if we wanted to. Okay, now we're going to move into logarithms. We're actually going to be touching upon them a little bit now. Now this is the thing to remember is right here. Y is equal to the log of ax means that x is equal to a to the y power, right? So the a is the base. If we think in terms of exponents, the a is the base, right? The y is the power, and the x is what it's equal to. X is what it's equal to. So another way of thinking about this is a to the y power is equal to x. Okay, so that's what we're actually going to be using. We're going to be using that power. Now all we're doing to begin with is we're simply converting everything over to logarithmic form. Okay, so let's scroll down just a little bit. So let's see. So again, the base, so we're going to say log, the log. Now, what's the base? Okay, so that's the base right there, right? And that's the base right there. So in this case, it looks like the 3 is the base. So we're going to say base 3. Okay, and then we say, well, what is it equal to? Well, it's equal to 9. So we put the 9 here. Okay, and then, well, what is the exponent? Well, the exponent is a 2. So we put a 2 there. There we go. So it says 3 to the second power is equal to 9. Or 3 to what power is equal to 9? 2. 3 to the second power is equal to 9. Okay, so let's move on to this one over here. All right, so now we're going to have to figure out what this is equal to so that we can put it in logarithmic form. So first of all, it's a negative exponent, so we're simply going to flip the fraction. So we're going to have a 5 over 1 to not the negative second power, but positive second power. 5 divided by 1 is simply 5. So we end up with 5 squared, which is equal to 25, right? Now, if we wanted to write this in logarithmic form, we put log, and what we could do is we could say the 1/5 base, and what is it equal to? Well, it's equal to 25. And what does that mean the exponent must have been? Well, the exponent must have been a -2, right? So 1/5 to the negative second power is equal to 25, and that's correct. Okay, so how about over here? Well, again, we're kind of going to have to do an extra step of figuring out what that's equal to, but now we can write it in logarithmic form, right? So what is the base on this? Well, the base is obviously 10. And what is it equal to? Well, it's equal to 100,000. And what was the exponent? 5. Now this one's a little bit different in that the default or understood exponent, right, I should say the base is 10. So if I just wrote a log here and I didn't write the 10, it would just be understood or implied that there's a 10 there. So I could do the same thing of just saying log. I could run 100,000 here. Oops. And then I would put it to the 5th power. That means the same thing, right? You don't actually have to write the 10 because that's the default. And later on, you're going to learn something about a natural log, and that's default is the constant e. Okay, so let's try this one right here. Again, we kind of have to take an extra step. This is understood to be over 1. You flip it to the bottom. I'm going over this kind of quickly now because we've done this for a while. This is 1 over 4 to the positive 3rd power. 4 to the 4 is 16 times 4 is 64, so we end up with 1/64. Okay, so if I was going to write this as a log, well, the base is going to be, right, it's going to be a 4. What's it equal to? 1/64. Right? And then, of course, what's the exponent? Well, it's a -3. So this would be 4 to the negative 3rd power is equal to 1 over 64th, or 1/64. Okay. So let's try a couple more of these. Solve each equation. Now, if you use what we just learned to rewrite this with exponents, you should be able to solve these. And this is what I mean by this. Remember before I would say this is like 4 to the negative 2nd power in this case is equal to x. All right, so we'd say 4 to the negative 2nd power is equal to x. All right, well, cool. So that would be, again, what we did before as a negative exponent, so we put it on the bottom. 1 over 4 to the positive 2nd power, which is 1 over 4 times 4, which is 16. So we would just simply say x is equal to 1 over 16. Not bad. Okay, so the next problem over here, same kind of concept. We're going to say, well, x, right, to the second power is equal to 3. Okay, well, fair enough. So in this case, we would simply take the square root of both sides. Now this is technically wrong because it's the principal or positive square root, but you can just kind of ignore that right now, and you end up with x is equal to the positive or negative square root of 3. Now there's nothing wrong with the algebra here, but in reality, generally speaking, you don't want x to be a negative number. So that's not actually positive. So you're just going to have a positive square root of 3 here. Okay, now this one's a little more complicated, right? Because we're basically saying, well, 1/2 to the second power is equal to 3x plus 1. That's fine, because once we square that, what we end up getting is 1/4. So 1/4 is equal to 3x plus 1. All right, so we want to get all the variables on one side, all the constants on the other. So minus 1, minus 1. 1/4 minus 1 is negative 3/4 is equal to 3x. Then we undo the multiplication of x by 3 by dividing by 3. And whatever we do to one side, we do to the other. So we divide that by 3. And we end up with x is equal to negative 3/12. Oops, 3/12. Okay, how about this one over here? So over here we're saying 49 to the x power is equal to the cube root of 7, right? So that's what they're actually saying right there. Okay, so again, 49 to the x power is equal to the cube root of 7. Now this looks really strange, and we probably need to do this new trick I'm going to show you, which is you get the same base. So if I do the prime factorization of 49, that's really 7 squared. Okay, now so if I did 7 squared to the x, the product rule would say that would be really equal to 7 to the 2x power. So I can simply rewrite this as 7 to the 2x power. Now over here I can also rewrite this as well, but this right here would be written as 7 to the 1/3 power. Now if the bases are the same, that means this exponent and this exponent must be equal to each other. So we simply end up with 2x equals 1/3. So simply undo the multiplication of x by 2 by dividing by 2. Whatever we do to one side, we do to the other. And we end up with x is equal to 1/6. Right? Okay, let's really quickly go back and simplify this fraction. My previous answer is bothering me. So let's divide both those by 3, and we'll get a negative 1. 12 divided by 3, 4, negative 1/4. Now, the argument of the logarithm can't be negative, but this negative 1/4, since it's being multiplied by 3, and then you're adding a 1, it's not going to be negative. So the x in this case can actually be negative. It just can't be so negative that it'll make this entire argument negative, right? Okay, so let's try to evaluate this one. So if I rewrite it, the base is square root of 2. It's to the first power and equal to square root of 2. All right, well, that's correct. That works. How about over here? We have 9 to the 0th power is equal to 1. That's also true. And over here, we have 0.2 to the 0th power is equal to 1. And we need to remember that anything to the first power is equal to itself, and anything to the 0th power is equal to 1. This pattern that you see in these three right here, that's going to come up again later on.